Alright, hello everybody, my name is Alessia, and I am the lead lecturer here at Pearl Street Studio. Welcome to our introductory lecture on hydropower. Hydropower is one of the many resources used around the world for generating electricity. So the goal of this lecture is to help people understand what exactly hydropower is, how hydropower is used to generate electricity, and discuss some of the considerations around using hydropower as an energy resource. But before I dive in, I did want to mention that this is Lecture 6 in our course Introduction to the Electricity Industry. If you haven't already, we recommend that you go back and watch our lectures on coal, crude oil, natural gas, geothermal, and nuclear, as this lecture references some of the material we went over in those lectures. No worries if you haven't watched them, we will add links in the notes to the YouTube video for our previous lectures, so you can find them there, but you can also find them by visiting our website at pearlstreetstudio.org. Alright, let's dive in. So, what is hydropower? Well, hydropower technologies use the energy from flowing water to generate electricity, which is a bit different from some of the other resources that we've talked about in this course so far. So how do hydropower technologies generate electricity? So all the different power plants that we've discussed so far use some sort of thermal energy to heat water, to turn it into steam, to then spin a turbine that is connected to a generator which produces electricity. But hydropower technologies use the energy from the flow of water moving downhill to spin a turbine instead of using steam. But one of the things that a term that I wanted to explain before I dive in, is the term gravitational potential energy. And what it is that when an item, or in the context of hydropower plants, water, is at a high elevation and has the potential to fall to a lower elevation position because of gravity, this means that it contains gravitational potential energy. So in a hydropower system, water is stored at a reservoir that is behind a dam at high elevation. So it has gravitational potential energy. And then when the operators want to produce energy, they release some of this water from this reservoir and allow it to flow downhill, which naturally converts the gravitational potential energy into kinetic energy. So how this works, this thing right here, this gray thing, which I've highlighted with my blue highlighter, is what is called a dam. So I'll label this as a dam. And behind the dam, which I have not sketched, will be a reservoir of water at a higher elevation. So, like I said, the operators, when they want to generate electricity, they let some of this water go through the dam, and as the water moves downhill, it gains that physical motion, which is the gravitational potential energy turning into kinetic energy. So there are then hydro turbines that are placed in the path of the water that take the kinetic energy of the water and convert it into rotational kinetic energy. So here, this is realistically more what a dam looks like, but if we have a simplified drawing here of what's going on, so water is flowing downhill here, and it's gained a lot of kinetic energy when it gets to the bottom of the hill, and that water then comes into contact with here a hydro turbine. And that hydro turbine, when the water flows, it spins the turbine. So the kinetic energy of the water is turned into rotational kinetic energy. So just the movement of rotating in circles. And similarly to the other types of power plants we have discussed, that hydro turbine, just like the steam turbines and the gas turbines we talked about, is connected to a generator. So I'll just label the generator here. Which takes that rotational kinetic energy and turns it into electrical energy. And then after, it creates electricity, which then is sent along power lines out into the electric grid to be used by all of us consumers. And the water, after passing through the hydro turbine, is then released into the river downstream. So that is at a high level how hydropower technologies generate electricity. Now I want to go over the different kinds of hydroelectric technologies. So there are actually a couple different kinds. So the first, there are three main types of hydropower. There is conventional, pumped storage, and run of the river. And first we're going to discuss conventional. And so here, a conventional hydroelectric dam generates electricity by storing water in a reservoir behind a dam, like we had discussed before. And here's a little simplified side view. It then releases the water through turbines to generate electricity. So here, there's this thing up here called the upper reservoir. Oops, my handwriting's a little messy there. Let me zoom in a little bit. Upper reservoir. So the upper reservoir stores water at a high location. So it's storing water that has gravitational potential energy. And then there's this little gray bar here, and this is the intake. And the intake moderates the amount of water that is allowed to flow downhill. And then when the operators open the intake, as the water flows from that higher elevation to a lower elevation, like I mentioned before, it picks up speed, converting that gravitational potential energy into kinetic energy here. So it picks up a lot of speed by the time it's right here. And then the kinetic energy from the falling water is then used to spin the hydro turbine, which I've showed before. Turbine there, which is then connected to a generator. And this can just be labeled as the electric grid. Grid here. And then the water, after it's passed through that hydro turbine, is then released downstream into what is also called the lower reservoir here. So that's generally how conventional hydroelectric works. Now, there's a second technology called pumped storage hydroelectric here. And pumped storage hydro is very similar to conventional, but it has the ability to pump water from the lower reservoir back up to the upper reservoir. So when electricity is abundant or inexpensive, the facility uses electricity to pump water uphill into this upper reservoir and store the energy as gravitational potential. And then when electricity demand increases, or maybe electricity is very expensive, the water is released from the upper reservoir to go through that turbine and then be deposited or released into the released downstream into the lower reservoir. Great, so that's how pumped storage works. And then actually let me label this here. So this is the electric pump. And that's the same here. Pump. Sending the water back up. Okay, awesome. And then the third type of hydropower technology is called run-of-the-river hydroelectric. So run-of-the-river hydroelectric is, again, similar to conventional hydropower, but it relies on the natural flow of the river rather than controlling the flow of the water from a reservoir through an intake. So if you notice here, there is no intake. It just allows the water to flow at whatever speed the river is naturally running at. So as water flows through the river here, all or a portion of the water is diverted through the turbines, which is over here, to generate electricity before being returned downstream. So because run-of-the-river facilities cannot control the water flow, their electricity production depends entirely on the river's natural flow rate, and can vary with each season, depending on the precipitation, snow melt, drought conditions, and all those kinds of things. Okay, so now that we've gone over the different types of hydro technologies, let's talk about some of the operational characteristics of hydropower plants. So, talking about their controllability. Conventional and pumped hydro storage plants are considered dispatchable generation resources because operators can change their electricity output in a matter of minutes just by adjusting the amount of water that is able to flow using the intake. But in contrast, run-of-the-river power plants are intermittent because their electricity generation depends entirely on the natural flow of the river rather than on water that's being stored behind a reservoir or behind a dam. So there's this new term here. We've discussed dispatchable. All the resources that we have discussed so far are dispatchable, but there's this new term here called intermittent. And an intermittent electricity resource is one that has an uncontrolled output. So it's typically based on weather and climate patterns. Okay, great. So now let's go to the fuel supply chain. So unlike thermal power plants, a hydropower plant doesn't require a fuel supply chain because they don't burn a fuel or use up a fuel to generate electricity. Instead, the quote-unquote fuel for a hydropower plant is the continuous movement of water supplies by the natural water cycle. So what happens here is that there is water that is in the clouds, and the precipitation from the clouds leads to rainfall and snowfall, which is collected in down on Earth in rivers, lakes, and reservoirs. And then the water that is held behind the reservoir is then let through the dam, flowing down to lower elevations, and then eventually, over time, the water evaporates and goes up into the atmosphere. And then in the atmosphere, the evaporated water condenses into rain or snow, which then flows back down to the earth as precipitation. So it's the water cycle, which we learned about ideally when we were younger. And so the availability of water can be significantly affected by seasonal rainfall patterns and droughts. Okay, then for fuel storage, you might be able to guess here. It's that upper storage or that upper reservoir. And in reservoir-based hydroelectric power plants, they store water by retaining it in the upper reservoir and closing the intake or reducing the amount of flow in the intake to be less than the flow that's coming in from the river further upstream. And so here, let's see, during periods where there's a lot of precipitation, like for example, maybe during the winter or the spring, there's a lot of rainfall, so water accumulates in that upper reservoir and can be stored for future use. And then in the seasons such as the summer, there's typically higher electricity demand in the summer because people are turning on their AC units. They can release more water through the turbines to generate more electricity. Then in comparison to the conventional and pumped storage, run-of-the-river plants typically don't have any storage and just rely on that natural flow of the river. Okay, capital costs and construction here. So hydropower projects require some of the highest upfront capital investments of any electricity generation technology, but still less than nuclear. Before construction begins, developers need to identify a suitable location that have significant water resources and a significant change in elevation for building out this reservoir and dam. And so because of these factors needing a sufficient water resource and enough elevation change, there are only a limited number of locations around the world that are suitable for hydro power development, and many of the best sites around the world have already been utilized. But But with that, let's go into the capital costs. So this data here, I got from Oak Ridge National Laboratory's existing hydropower asset database. That is a long phrase. But Oak Ridge National Laboratory is a laboratory in the United States. And then I also got this data from the U.S. Department of Energy's Hydropower Market Report for 2023. So these values here are in US dollars from 2022. So there's quite a range on the capital cost of these plants. Conventional hydropower plants run in the range of $2.6 to $16 million per megawatt and have a typical size of 35 megawatts, which means that the average cost of building out these power plants, if we take a middle number between these two, is about $320 million. Now for pumped storage tends to be much larger in the United States. It does range from about 2 to 5.5 million per megawatt, but the size here you can see averages at about 510 megawatts. Now taking an in-between number of these values, the average cost of building out a pumped storage facility is about $1.8 billion in the United States. Now it can vary from country to country, but I was just using the United States as an example here. Okay. And then for the operational costs, so once a hydropower plant has been constructed, its operating costs are relatively quite low because it doesn't require any fuel to generate electricity. And so this range of values I have here, this $8 to $42 per megawatt hour, is derived from the National Renewable Energy Laboratory's annual technology baseline report from 2023. That's a mouthful, but that's a laboratory that is located in the United States, so these numbers are for the US. The value is in US dollars in 2022. But the average, I realized I spelled average wrong. Let me change that, let me fix that. Oops. Average, there we go. The average, from that I calculated, derived from this report, was about $16 per megawatt hour. Now, if you remember the numbers that I had said with some of the other energy resources, operationally, hydropower is the cheapest of the resources that we've discussed so far. So even though it can have these very high upfront costs to build these power plants, its electricity costs a lot less than these other resources. Okay, now for air pollutants and greenhouse gas emissions. Now, one of the great parts about hydropower plants is that they generate electricity without burning a fuel. There's no combustion reaction, so they don't emit any air pollutants, and they do emit a negligible amount of greenhouse gases during their operation. But that's from something other than combustion. But this means that hydropower is one of the lowest emission sources of large-scale electricity generation and can help to significantly reduce air pollution and greenhouse gas emissions from the electricity sector. Now, it's great that they have very low operational emissions, but the construction of dams and reservoirs can have a very significant environmental impact on local ecosystems, waterways, and wildlife. I'm not going to go into those details here, but these impacts will be discussed in greater detail in Unit 4 of this course, Environmental and Social Impacts. Okay, and then the last part of this subsection is role on the electric grid. So conventional and pumped storage hydroelectric power plants are among the most flexible electricity generation technologies because they have the ability to operate as baseload, intermediate, or peaker power plants. On the other hand, run-of-the-river power plants have much less operational flexibility because their electricity just depends on the natural flow of the river. So here you can see this similar chart that I have shown in the other lectures. I'll change this to blue or to green here. The x-axis is time of day. The y-axis is the electricity demand or generation in megawatts. So here, this is a typical electricity demand curve from consumers. And here I just illustrate in these different shades of blue here what are the different operational patterns for hydropower. So it can be operated as a baseload, similar to nuclear, coal, and geothermal. It can operate as an intermediate resource similar to combined cycle natural plants, and then it can also operate as a peaker load or a peaker power plant. Pardon my, I misspoke there. A peaker power plant, similar to a simple cycle natural gas power plant. So, but one of the big caveats, as I alluded to before, is the ability of hydropower plants to provide reliable electricity is very heavily dependent on water availability in a region. And this makes hydropower plants vulnerable to the impacts of climate change. So climate change has led to changes in precipitation patterns, prolonged droughts, reduced snowpack, earlier snowmelt, among many other things. And it can reduce the amount of water stored in reservoirs that's available to generate electricity. So in some regions, these changes have already had a very significant impact on electricity production. And one of those examples is the Colorado River Basin. This is over in the United States. It has lowered the levels of a lake called Lake Mead. And this lake is the reservoir that's behind one of the huge hydropower plants called the Hoover Dam in the US. And unfortunately, it has significantly reduced the capability of this power plant, or of this hydropower plant, to generate electricity because the water levels are so low. All right, let's go to the last section, geopolitical considerations around building hydroelectric power plants. So the first one is energy independence. So hydropower can provide a degree of energy independence by allowing regions and countries to generate electricity using locally available water resources rather than relying on imported fuels, which is the case for like crude oil, sometimes for coal, for natural gas, and for nuclear. Now, one of the cool examples is Iceland. According to the International Energy Agency, Iceland produces 68% of its electricity from hydropower, which is super cool. And that other 32% is from geothermal, which we mentioned back in our geothermal lecture. So from a power plant standpoint, Iceland is a very unique and interesting place. Okay. The third geopolitical consideration is control over shared water resources. So conventional and pumped storage hydro facilities can alter the timing and flow of water through rivers. And this can affect the availability of water for regions that are located downstream from the power plant. So when a river is impacted by a hydroelectric power plant and it crosses national borders, the dam can become a point of political tension between countries with competing interests. So an upstream country wants to control that water flow in order to support electricity generation. But downstream countries may view this as a threat to their water security and their agricultural industry if they use that water resource for it. So to promote the cooperative management of these waterways that hydropower plants are dependent on, countries will often establish what is called a transboundary water agreement that balances the benefits of hydropower development as well as the water security and agricultural needs from downstream regions. So I have two examples here. The first one is the Itaipu Treaty, that governs the construction of a dam called the Itaipu Dam between Brazil and Paraguay. This dam is located on the Parana River, and this river forms the border between these two countries. So they've figured out a way to balance these resources. But an example of a more recent example, where there is still some political tension, is the hydropower project that is currently in development in China, called the Midu Hydropower Project. This project is being built out on the Yarlung Tsangpo River. This project has raised a lot of concerns downstream in India and Bangladesh about potential impacts to water availability in these two countries. Okay, and then the third one is community displacement. So large hydropower projects often require creating these massive reservoirs, which are, in order to create a reservoir, it requires flooding extensive areas that are upstream of the dam. And as a result, there can be local communities that might be displaced from their homes, and cultural, historical, and archaeological sites can be lost beneath the reservoir. And so not only does it impact the people that have lived around this reservoir for maybe hundreds or thousands of years, but it can also alter ecosystems, disrupt fish migration, and affect the livelihoods of the people who depend on this river source for fishing and agriculture. One of the examples of where this has been very contentious from a community displacement standpoint is the Bakun Dam that is in Sarawak, Malaysia. And when this dam was built out, it resulted in the displacement of more than 10,000 indigenous people from their ancestral lands. Okay, that is it for our hydro lecture. Thank you so much for watching. This is the first version of our hydropower lecture, and we know that there's probably much to improve here, so we would love your feedback. Is there something that wasn't explained clearly enough? Do you think there's other information that we should add? We will be adding a link to a feedback form in the notes, and after we receive a sufficient amount of feedback, we will update the lecture, we will re-record, and post the updated video. So for those of you who will be providing feedback, thank you so much for helping to improve the quality of publicly available education. Also, if you found this lecture valuable, please consider donating to help us continue making publicly available educational content on the electricity industry. We'll be including a link in the YouTube notes, but you can also donate by visiting our website, pearlstreetstudio.org. Okay. Well, that's it here, and see you at the next lecture.